continuing with these max-min problems, let's take a look at this one. Okay, these are getting a little bit more complicated here. Not conceptually complicated, but the computations and the next 2 or 3 of them are a little more interesting. Exercise 42 says, a cone is formed from a circular piece of material of radius 1 meter by removing a section of angle theta and then joining the 2 straight edges. Determine the largest possible volume for the cone. Okay. You might want to think of this almost as a dynamic problem, as kind of you do with all of these max-min problems. If theta is really small, or even 0, then you're producing a really small volume cone, or cone with 0 volume, if we take theta to be 0. So if we don't cut out anything here, we get just a flat disk, which has height 0, if we try to treat it as a cone. If we cut out a narrow little sliver, then we're going to get a cone with a large base radius, but not a very big height. If we cut out a whole lot, so maybe we make theta a little bit less than 2 pi, and we actually take a little slice here, then you're getting a really tall cone, but the base radius will be really small. So it's a balancing act between the two. The volume is 1/3 pi r squared h. So like in the previous discussion, see the r gets squared, I would expect it to carry a little bit more weight than the h. But intuitively, giving an idea of what the answer is, I got nothing. I need the calculus stuff. But here's the plan. So we've got a situation where we started with a disk of radius 1. We've removed this sector, glued these 2 straight sides together to create a cone. This slant distance will be 1. The height we'll have to compute, and the base radius we'll have to compute. But I think I see, as we had before, a right triangle with height h and this other dimension is r. So we'll have an h squared plus r squared equals 1 squared. There's a right triangle embedded in this cone, just like there was in the previous cone problem. Okay, step 1, we read the question. Steps 2 and 3, draw a picture. So let's use their picture. And let's introduce height h and radius r of the cone as variables or as unknowns. Then we'll have, it's just commented, we'll have h squared plus r squared equals 1. We've got a right triangle here. They've got the right angle there. Here's the height. They didn't draw the radius in, but the radius, I'm talking base radius of the cone, not radius of this disk over here. Base radius of the cone will denote as r. Right triangle, h, r, hypotenuse 1. Pythagoras tells you this. We could solve for r or h. By the way, if we solve for h, we get the square root of 1 minus r squared. It's a plus or minus, follows from the equation, but of course h is a distance, and so I don't take a negative square root. Okay, we need to relate the variables, and that's a little tricky in this one, but follows as given here. The circumference of the base of the cone, so I'm looking at the distance around the base of the cone, is 2 pi radius. And the base is a disk of radius lowercase r. Okay, circumference of a circle of radius r is 2 pi r. So the base, I'm not talking about the circle, the base of this right circular cone is a disk of radius r, a circle of radius r, and so the circumference is 2 pi r. Well, this equals the length of the arc subtended by the angle 2 pi minus theta. The rest of the angle here, the part we kept, it's 2 pi radians all the way around. We've removed pi radians and created this thing here. This thing here has a central angle of 2 pi minus theta. The other theta is in the part removed. So let's compute the distance around here. the distance around this modified disk will be the same as the distance around the base of the cone. And that's how we'll get a relationship between theta and everything else. Let's see, so the length of the arc subtended by 2 pi minus theta in the circle of radius 1. What is that? Well, that'd be that would be central angle times radius, right? We had 2 pi r, well, it's because we went all the way around that other circle. This time we're going 2 pi minus theta of the way around, if you will. The central angle is 2 pi minus theta. The radius of this circle is 1. So the distance around here is 2 pi minus theta times r. If you want to do that more slowly, the distance all the way around the circle would be 2 pi times 1, 2 pi times the radius of this. And then the little part that we left off, remember how you measure arc lengths around a circle, would be, since we're measuring the angle in radians, would simply be theta times radius. Theta r, the radius of this one is 1, it'd simply be theta. So no matter how you slice it, you get 2 pi minus theta as the distance around. I could take the total distance around 2 pi and subtract this little bit here, theta, and we get 2 pi minus theta. Or we could measure it in terms of the central angle, 2 pi minus theta multiplied by radius, you still get 2 pi minus theta. We'll take theta to be between 0 and 2 pi. Let's include the endpoints. When theta equals 0, we didn't make a cut at all. We didn't remove anything. And so the resulting cone has height 0 and volume 0. I'm okay with that because, as you've seen, I want to get endpoints so I don't have to do some first or second derivative test stuff. Theta equals 2 pi means we basically cut out the whole disk and we've got nothing left, which results in a volume of 0 as well. But let's include those endpoints. You might argue about their physical meaningfulness. I'd say, I might agree with you there. Their mathematical meaning is pretty solid, though, and it gives me endpoints, so I don't have to worry about anything other than critical points and endpoints when the time comes. So we've got the circumference here, which was 2 pi lowercase r, equals the distance here, which was 2 pi minus theta. So we must have 2 pi r equals 2 pi minus theta. That sets up a relationship between r and theta. If we solve this for r, divide both sides by 2 pi, we get 1 minus theta over 2 pi. Divide both sides by 2 pi, we get some cancellation there for the 1. Ooh, and if we got r, we can find h as well. So we can find everything in terms of theta. We're ultimately looking for a function that expresses the thing to be largest, maximized, the volume of the cone. So we want to write the volume of the cone as a function of theta. So that's why we're doing what we're doing. Okay, so we've got r in terms of theta. We had h in terms of r as well. So h was 1 minus r squared. We just saw r was 1 minus theta divided by 2 pi. So we'll plug that in there. I didn't promise you any pleasant algebra in this. This multiplied out, I may talk through some of the algebra because there's quite a bit of it, and leave it to you to pause the video and convince yourself you believe the algebra, or look up these notes posted online and convince yourself of the algebra. Squaring produces this. The subtraction, we lose the 1. Some signs change upon distributing, gives us this. Here's h in terms of theta. So we've got r in terms of theta. There it is in those parentheses. And we've got h in terms of theta. There it is. So far, so good. Haven't done any calculus yet. Do you see any calculus concerns coming up? Yeah, you know, I wish that square root wasn't there, but I think we're stuck with the square root. No matter how you do this, you're stuck with a square root in this one. Okay, well, I know how to differentiate square roots. Okay, volume of the cone. Step 4, we're looking for the quantity to be maximized in this case, and that's the volume of a cone. The volume of a cone is 1/3 pi r squared h, where the r and the h are the radius and heights, respectively, of the cone. And we've got both of those things, r and h, in terms of theta. So we'll just plug them in. So the volume as a function of theta is 1/3 pi r squared. Well, r squared, here's r squared right here. Right? We had substituted in. Here's r squared, 1 minus theta over 2 pi squared. H, we had h expressed here with this square root stuff. So there's the volume of the cone as a function of theta. Let's see if we can't clean it up a little bit, because we're going to have to differentiate this thing. Okay, so let's see. We could get a common denominator here and write this as 2 pi minus theta over 2 pi. Take the 1 and write it as 2 pi over 2 pi. I mean, we just did something backwards from that previously. Let's write this quotient like this. This is part of the simplification process. Here, let's get a common denominator of 4 pi squared. So we'll multiply this by 4 pi over 4 pi, giving a common denominator of 4 pi squared. First term will be 4 pi theta, 4 pi theta. Second term minus theta squared. Okay, let's get rid of some of this fraction stuff because we can. These are just numbers. Here we've got a squaring. We've got a 4 pi squared we could bring out here. Here, taking a square root, we've got a 2 pi we could bring out. So let's do that, leaving us with a 2 pi minus theta squared. There that is. The numerator under the square root. There that is. And let's see, I just need to make sure we got the right number of pi's. We had, what was it? 4 pi squared here. Okay, that'd give us a total of 12 pi squared. We're going to bring out another 2 pi. That'd give us 24 pi cubed. So bring those pi's out front, those constants out front. This can be further simplified, so we can cancel one of the pi's to get 1 over 24 pi squared. And let's write that square root as a 1/2 power, because we're going to be differentiating. But there's volume as a function of theta, and it's about as simplified as we're going to get it. All right. The question was maximize volume. So in terms of what we've introduced, the question is find the maximum of V of theta, as given above, for theta in the interval from 0 to 2 pi. We good? That's the setup. So that's turning the words into formulas and the formulas into a function and the question into a calculus question. So no calculus until now. I say this is the easy part. Okay, although the algebra on this one's going to be a little unpleasant. We'll find the derivative, we'll check critical points, and we'll check endpoints. That's the calculus concepts. So that's a piece of cake. Okay, the derivative, well, let's see, we'll have to use a product rule, and it looks like there's a couple chain rules in the mix. We'll take the 1 over 25 pi squared, parentheses, just bring that all the way out front and differentiate this product. So we'll have the derivative of the first. Well, it's raised to a power. So we'll bring the exponent of 2 down, rewrite the inner, subtract 1 from the exponent, getting an exponent of 1 and not writing it, and multiplying by the derivative of the stuff inside. It's a function of theta. We're differentiating with respect to theta. 2 pi minus theta has a derivative with respect to theta of -1. Close those square brackets off. There's a derivative of the first. Rewrite the second, plus the first, right? The first times the derivative of the second. Same story pretty much. Bring the exponent out front, rewrite the inner, subtract 1 from the exponent. 1/2 minus 1 is -1/2. And then the chain rule says multiply by this derivative of the stuff inside. 4 pi theta minus theta squared has a derivative of 4 pi minus 2 theta. And there's a derivative. All right. So we want to see when that's 0 and when that's undefined for theta between 0 and 2 pi. Okay, so let's see, what do we do? Clean it up a little bit. Yeah, let's see. We've got a -2 here. We could factor a 2 out of this and cancel it with a 1/2. That'd leave us with a, what, a 2 pi minus theta. We've been seeing lots of 2 pi minus thetas. And I believe that's what we did. Let's see, awkward place for a line cut. So we've got a -2 from this one. We have a -2 out front. Yeah, there's a -2. Okay, and this has changed a bit. It now reads 2 pi minus theta. Let's go back. Yeah, we factored a 2 out of this, canceled it with that 1/2, and here we'd have a 2 pi minus theta, right? A 2 pi minus theta we'll have in the numerator, and we could push this to the denominator. It's -1/2 power, so take it to the denominator as a square root in the denominator to the 1/2 power. So that's the algebra that ties those two slides together. So we've cleaned it up a little bit. What you're going to do now, and the ultimate goal is to factor the derivative so you can see where it's 0. I got these square roots. I'm worried about it maybe being undefined as well. And we got some denominators that we didn't have in the original function. Let's get a common denominator that you commonly do in trying to factor. So the common denominator between these two terms would be this denominator. So we'll take this term and multiply it by this denominator divided by itself. How convenient. The denominator is this term, so we'll get this term squared. I lose the square roots, divided by the common denominator, plus the second term over here. Pause the video and convince yourself of the algebra. It's the algebra that's tedious in this one. Now we've got a common denominator. This can be simplified. So let's see, we've got a -2 times this stuff will give us -8 pi theta plus 2 theta squared. Let's square this out. That'll give us the first one squared, which is 4 pi squared, minus twice the product, 4 pi theta plus theta squared, multiplying it out. Let's take this 2 pi theta and stick it in a numerator over here. Let's bring this thing out front, put it in a quotient also. So let's simplify this. We've kept the 2 pi minus theta. There it is. There's a 24 pi squared. There's that square root stuff. This simplifies as, here's a 2 theta squared. There's another 2 theta squared for a total of 3 theta squares. Minus 8 pi theta minus 4 pi theta for a total of minus 12 pi theta in the 4 pi squared. There's the derivative, and there's a derivative almost factored. So where is this 0 or undefined? All right, it's not completely factored because we got a second degree polynomial here. We'll deal with this on the next page. But for now, for critical points, first, the endpoints, 0 and 2 pi, are critical points. When theta is 0, we got a 0 here and we got division by 0. And 0 was in the domain of the original function, so it counts as a critical point. It was already important because it was an endpoint, but by the way, it's a critical point because the derivative is undefined there and the function is defined there. 2 pi is a critical point because that makes the derivative 0. This term would be 0, and so the whole thing would be 0 when theta equals 2 pi. So there's 2 critical points. For the record, they were already important because they were endpoints. What's up with 4 pi theta minus theta squared? You worried about square roots and negatives? Yeah, if you got them here, you probably got them upstairs. But we're keeping theta between 0 and 2 pi. And for theta between 0 and 2 pi, this is non-negative. It's 0 at the endpoints and it's positive in between. So, right, it's 0 at 2 pi, we'd have 8 pi squared minus 4 pi squared. I take it back, it's not 0 at this endpoint. It is at the theta equals 0, but it's non-negative throughout. So there's no square roots and negatives. There's a square root of 0, that's not a problem. but it's in the denominator, and that is a problem. So theta equals 0 counts as a critical point. There are no critical points that result from square root of negative concerns. So we don't have that to worry about. So we've taken care of this factor. We've taken care of this factor. Now for this last factor. All right, and where do we stand? 2 critical points, and they're both endpoints. So nothing new of any concern there, but we did have to check those details. Here's the derivative. What's up with that second degree polynomial? So if we set the derivative equal to 0, then we either get this equals 0, which we've already dealt with, theta equals 2 pi, or this equals 0. So we'll set that factor equal to 0 and use the quadratic equation. A theta squared plus b theta plus c. Okay, you got thetas instead of x's, but I can still apply the quadratic equation, and we get theta equals negative b, coefficient of the first power, it's negative 12 pi, plus or minus b squared minus 4 ac. A is 3, c is 4 pi squared, all divided by 2a, and a is 3. The things in parentheses are the a's, b's, and c's, things I've substituted for, as I try to consistently do. If you'll follow through the algebra, so this is straightforward, but it reduces to 2 pi plus or minus 2 on the square root of 6 over 3 pi. All right. Not a clean number, but anyhow, there's what you get for the other critical points. Are these in the interval 0 to 2 pi? We've got 2 pi plus something or 2 pi minus something. Well, if you take 2 pi plus something, you're not getting something in the interval 0 to 2 pi. It's too big. 2 pi minus, as long as this number isn't too big, and it's not, 2 square root of 6 over 3, that's not as big as 2. So we are indeed getting something that's in this interval when we do the subtraction. So theta equals 2 pi minus 2 square root of 6 pi over 3. That gives a critical point. So we've got a critical point of 2 pi minus 2 square root of 6 pi over 3, a critical point of 0, and a critical point of 2 pi, and an endpoint of 0 and an endpoint of 2 pi. So we need to check the volume formula at 0 and 2 pi. That's going to be a total piece of cake. And at this angle here. You might be rightly concerned about what this is going to lead to, because this has got to go into that original volume function. But we had a lot of 2 pi minus theta stuff in that original volume function. So when we do 2 pi minus theta, this 2 pi is going to disappear. So let's see what happens. So where we are is we need to plug into the volume function for the record. There it is. We need to plug in 0. When you plug in 0, you get 0 out because of this term. We need to plug in 2 pi. You get 0 out because of this term. And we need to plug this thing in. Plug this thing in. All right, I told you we had a 2 pi minus theta in there. So we'll get 2 pi minus this thing, quantity squared, the leading coefficient. That's could be worse. The 2 pi's cancel, and we're left with 2 square root of 6 pi over 3, and that gets squared. We'll even lose the square root. I mean, there's numbers flying everywhere. On this part, let's see, we had 4 pi theta, so we'll have 4 pi, that value, that critical point, minus theta squared minus that critical point squared. Here's the algebra. It's not hard. It's distribution, squaring, and being very careful with the distribution of that negative sign. Produces this, which upon simplifying, actually simplifies down quite easily. I leave it to you to deal with the algebra that links this to this. Maybe I can at least convince you that there should be pi there. Here's a pi squared. When we square this, there's another pi squared. Those cancel. Hey, look, there's pi squares in all of these terms. We could factor pi squared out of those terms, and that's under a square root, so that'll produce a single net pi to the first power. So the pi's are gone. That's why there's no pi's in this. We've got some cancellation here with these terms. These two terms cancel. We're left with this thing over here. So that's where the 24 over 9 came from. The 8 minus 4 is where the 4 came from. And then we've multiplied this out and simplified with a 24 in the denominator. Trust me, or pause and try to think through the algebra. But that is correct. And this can be rewritten without the 1/2 power, but instead as a square root. We've also got a common denominator here, simplified some more, dealt with some square roots, and we produced this thing here. All right, where are we? We're at the last step. We've checked the volume function at the endpoints. There were 2 of them, and the critical point. Which is bigger? 0, 0, or 2 on the square root of 3 over 27 times pi? Well, it's that one. So the maximum volume is that in cubic units, whatever in the world of units were. They never told us. So cubic units, I kind of wish they'd give us units to get us in the practice of that. And this occurs when theta takes on that particular value there. I told you it wasn't intuitive. For these kind of problems, this is what passes for nice numbers. Because there's a Pythagorean theorem in there, there's probably going to be square roots in there. And that square root stuff cascaded through the differentiation process, it cascaded through the algebra, and it even made a little appearance in the final answer down here. It even makes a little appearance in the input value there. So I see square roots. But the maximum volume is given by this quantity, and conceptually, we did the same thing. Wrote the desired quantity as a function, and fortunately, we had a closed and bounded interval, so we checked the endpoints and the critical points. Same thing we've done several times before. Let's do another one. Okay, this one's a little bit different. These things with cones and cylinders, there's cone problems in the book as examples. Those are really standard problems. This one's a little unusual and says, 2 masses hanging side by side from springs have positions S1 equals 2 sine t and S2 equals sine 2t, the locations of the 2's being vital, of course, respectively. So they've drawn a picture. This is a little odd one to draw a picture of, but the idea is S1, the displacement from some equilibrium rest position, they usually call it with springs. We've got a displacement at time t of course for time, given by S sub 1 for this one and S sub 2 for that one. They've introduced an axis here, a vertical axis, S axis, since they're using S for position. Using S for position is actually fairly common. They got the axis pointing down, which is a little odd, but all right, that's how they've set things up. At what time in the interval t greater than 0 do the masses pass each other? Okay, that'd be when S1 and S2 are the same, right? The 2 masses are going to wobble back and forth and pass each other at various times. When does that occur? That's not a calculus problem, that's a trig problem. And they give us a little double angle formula sign hint here, so that must pop up in the computations. All right, all's well and good. Secondly, part B, when in the interval 0 to 2 pi is the vertical distance between the masses greatest? And what is that distance? Okay, so that's a calculus question. They're asking us to maximize distance between the 2 masses. And they give us a double angle formula hint on that one also. Okay, so first, when do they pass each other? Well, that's just when their displacements are the same, when S1 and S2 are the same. So we'll set S1, 2 sine t, equal to S2, sine 2t. We'll set those equal to each other, which can be written as 2 sine t equals 2 sine t cosine t, using that double angle formula hint. Sine 2t is 2 sine t cosine t. So substituting this in for the right-hand side of the equation produces this, which we can rearrange and factor. That's how you solve equations. Factor and set it equal to 0. We get 2 sine t times 1 minus cosine t equals 0. So we either need sine t equals to 0, or this thing equals to 0, which would mean cosine t equals 1. So we've reduced it down to solving these two questions. Sine t equals 0, need to depend on your knowledge about sine functions, means the input must be an integer multiple of pi. So sine t equals 0 implies t is an integer multiple of pi. They wanted us to do this for all n, or all t greater than 0. I've actually given an answer for all t down here. It's easily modified. Cosine t equals 1. That happens at even multiples of pi, at 0, at 2 pi, at 4 pi. That cosine function reaches the crest of a wave. It starts at the crest of a wave, if you like, when t is 0. So the masses pass each other when t is some integer multiple of pi. Here we had all integer multiple of pi. Here we had even integer multiples of pi. Well, all multiples include the even ones and the odd ones. So we can express it in terms of this. I see an ever so slight mistake in my write-up. They wanted t greater than 0. So I need to take natural numbers down here. I need to take n to be greater than 0 to answer the question they asked. So that's an ever so slight error. I think I'll leave that in the notes, though. That's when they pass each other, past, present, or future. All t values, actually. But that's not what they asked for. Let's do the calculus problem here. So the next part is, when is the vertical distance between the masses greatest? All right. It's a max-min problem. Step 1, read the problem, done. Steps 2 and 3, draw a picture, and they gave us a picture, introduce variables. You know, they gave us variables. They gave us functions of certain things. They didn't give us the function that represents the distance between the masses, but that's easy enough. That's the absolute value of S1 minus S2. Oh, absolute values. Okay, we're going to work around that. In terms of t, the distance between the masses is, well, S1 was 2 sine t, S2 was sine 2t, so I substitute in. There's what we get for the distance between the masses as a function of time. It's got absolute values in it. We can't differentiate that. But I tell you something we can differentiate. The absolute value is not differentiable. Let's take distance squared. If we minimize distance squared, then we've minimized distance. So let me denote this function as d sub 2. It's kind of like distance squared. I don't want to use a superscript. That usually means other things. D sub 2 of t, let's take that distance and square it. It produces this, that, right? I can drop the absolute values because I know when I square something, it's non-negative. That I can differentiate. So we're considering distance squared instead of distance. That's a little nuanced piece of this one. We'll call it d sub 2 of t, and we want to maximize d sub 2 of t. That's not the maximum distance. That's the maximum of the distance squared. They wanted us to know what is the distance. Okay, I'll have to be careful with that. I'm finding where the distance, when the distance is maximum first, and then we'll figure out the distance. It won't involve this function, it'll involve this function, which is the square root of this function. So we'll have to take square roots to answer part of this. So I say consider this because we can differentiate it. It's an increasing function, and for non-negative inputs, it produces inequalities. It preserves inequalities. So if we differentiate this function, okay, composition, bring the 2 out front, rewrite the stuff inside, use a chain rule, derivative of inside, derivative of sine is cosine, derivative of sine is still cosine, except we've got 2t inside, so chain rule, again, spits out a 2. You're good at differentiation. So let's not belabor that too much. which can be simplified a slight bit by bringing this 2 out front to give us a 4. Rewrite that and rewrite the, oh, sorry, I brought both of those 2's out, excuse me. Bring those 2's out front, as I would have to do. And that second term becomes cosine t minus cosine 2t. We're going to set that equal to 0. Whoops, didn't mean to go just yet. We're going to set that equal to 0. That'll imply each of these terms is 0. And we'll see what we get from there. So we've got the derivative. When is this 0? We know that's 0 when t is an integer multiple of pi, because that's what the first part was. So this occurs, we've already solved this equation upstairs. 2 sine t minus sine 2t equals 0. That was part A. And we saw we get t as an integer value of pi. We're interested in the interval 0 to 2 pi this time, so we'll take 0, 1 pi, 2 pi, and that is all to stay in the interval. That takes care of the first factor. Second factor, cosine t minus cosine 2t, we want to set that equal to 0 and see what that implies. Well, hey, cosine 2t is 2 cosine squared t minus 1. That was a hint. So they gave us the hint of this double angle formula for cosine. That's where this comes from. We mentioned it in passing in chapter 1 when we were doing review material. But take the cosine 2t, replace it with this. Now we've got nothing but cosines here. So that gives us cosines of t. That gives us negative 2 cosine squared t plus cosine t minus a negative. That would be plus 1 here at the end. Hey, that's a polynomial in cosine, and it factors. It factors into 2, negative 2 cosine t minus 1 times cosine t minus 1. Foil it, and you'll see that that is indeed correct. Again, I trust you to pause and double check the algebra. It is correct. But factoring. So that leads to 2 things set equal to 0. The first one, negative 2 cosine t minus 1 equals 0. Or the second one, cosine t minus 1 equals 0. Solving the first one reduces down to cosine t equals negative 1/2. Cosine t equals negative 1/2. Need to know the angles between 0 and 2 pi that satisfy that. I'm leaning on your previous knowledge of special angles. Certainly negative 1/2 is what you get out when dealing with special angles from sines and cosines. And the corresponding angles in the interval 0 to 2 pi are 2 pi thirds and 4 pi thirds. Got to lean on your background for that. The other part, cosine t equals 1 is what we're dealing with, implies t equals 0 in the interval from 0 to 2 pi. T equals, actually t equals 2 pi works as well. Should include both of those at this observation. We've already got the 2 pi included, but yeah, I should include it here for completeness. So, closed and bounded interval, we found critical points and endpoints. The endpoints were 0 and 2 pi. In addition to those, we had the critical point pi, the critical point 2 pi thirds, and 4 pi thirds. Yeah, that's in the interval 0 to 2 pi. So we need to check 0, pi, 2 pi, 2 pi thirds, and 4 pi thirds. And let's see what happens. We're plugging into the d sub 2 function. You plug in 0, pi, or 2 pi. All those are going to produce 0. I've left some trig steps out. All of those produce 0 though. So we'll get 0 out for those. Does that make sense? That's when they were passing each other. I already knew they were passing each other at 0, pi, and 2 pi. Oh, that's why. The distance between them is 0. So that's not a surprise in light of part A of this problem. We plug in 2 pi thirds and 4 pi thirds, and we get out, well, again, I'm going to leave the trig to you. We get out 3 squared to 3 over 2 squared, and negative 3 squared to 3 over 2 squared. Of course, the negative gets absorbed. We get the same thing out at both of those. So I picked the larger of these values, and the values are 0, 3 squared or 3 over 2 quantity squared, and, well, effectively 3 squared or 3 over 2 quantity squared, and that's the biggest. So D2 has a maximum at both 2 pi thirds and 4 pi thirds, and that maximum is, okay, so we're going to plug those values into D sub 2, but that's not the distance, that's the distance squared. So we'll have to take a square root of that. So we'll have to take a square root of this quantity squared. Remember, when you take a square root of something squared, you get the absolute value. Fret not about that negative sign there. It's lost in the squaring process. And at both points, we get 3 squared or 3 over 2 for the distance between the two. So it was the same as the other, except it involved trig functions. It was find a function that expresses the distance between them. We tweaked that a little bit for some technical reasons. Can't differentiate absolute value was the technical reason. And then we found critical points and endpoints. And we checked the critical points and the endpoints and took the largest. So same technique. All right, this one's going to take a second. Standard Calculus 1 problem. It's even got a name, the ladder problem. So here's a story. What's the approximate length in feet of the longest ladder you can carry horizontally around the corner of the corridor given in the picture on the right? Round your answer to the nearest foot. Well, we'll do it exactly, and then we'll have to pull up a calculator to numerically approximate, and then we'll do the rounding down. But we'll do this exactly as we should. So here's the idea. We've got a hallway here that's 8 feet wide, and it's got a corner in it. It's only 6 feet wide going down this part. So the question is, how long a ladder can you get around the corner? Sometimes it's talked about in terms of getting a couch around a corner. Here's a hint, this is my hint. Write the length of the ladder that's wedged into the hallway as L equals L sub 1 plus L sub 2. Introduce an angle theta given in the picture here. Then find the minimum value of L to determine the longest ladder that'll pass around the corner. Okay, we're introducing this angle theta, is given here. L1, the length of the ladder stuck here, and L2, the length of the ladder stuck there. We're trying to get this ladder around the corner. If it won't go around the corner, this ladder's too long, and it doesn't look like this one will go around the corner. You can't, let's see, I got it wedged in there. I want to think of it as too long so that it's stuck. In my picture, I can't actually tell how it got stuck in there, but maybe I can't push it any further in this direction because the corner makes it not allow rotation any further. But the reason we're finding a minimum value with L is we're finding the minimum length ladder that'll go around the corner. We're finding the minimum length here that results, and any ladder of that length or shorter will go around the corner. Any ladder longer than that will get stuck. That's why we're minimizing the sum of L1 and L2. That's the plan. This one's a tricky idea to set up. That's why I wanted to add this as a hint. But I see right triangles and I see thetas. Excellent. That means probably some trig function stuff because we're talking lengths. Right? We're talking hypotenuses in these right triangles, and we're talking this angle theta. So I expect to see some trig functions. The Pythagorean theorem, maybe. I'm thinking trig functions because angle theta has been introduced. Trig functions are certainly possible. Here's a right triangle with hypotenuse L2. This distance is 8, and we could figure out that distance. You know, that distance, not of particular interest. We'll be discussing the range over theta here in a little while. What could theta be? Could theta be 0? If theta were 0, that would correspond to rotating this ladder around so that it was flush with this wall. I mean, that'd give us an infinitely long ladder. It gets stuck right there, say. Can theta be pi halves? Well, it's the same kind of problem, except now you'd have the ladder lying, the infinitely long ladder lying against this vertical wall. So we want theta between 0 and 0 and pi halves, 0 and pi halves. And we don't want to include the endpoints. We don't want to include theta equals 0 because that really doesn't make physical sense. And we don't want to include theta equals pi halves. And also those correspond to infinitely long ladders. Well, that ain't going to give us a minimum value of L. So we'll do this over the interval 0 to pi halves. But we won't have endpoints. All right, so we'll have to do some first derivative test or second derivative test. Here's a physical problem where you don't get closed and bounded intervals. And you'll see why I'm so happy in the previous ones that we had closed and bounded intervals, even though I may have done some mathematical stuff that you thought was physically suspect by referring to cones with a height of 0, or radius of 0. Yeah, well, it gave me endpoints and we didn't have to do what we're about to have to do. All right, so there's our picture. So we'll take this as the picture part. Theta's been introduced. In fact, it's L1 and L2 we're interested in, ultimately interested in getting the length of this ladder as a function of one variable. That variable will be theta. Well, like I said, it's a couple of right triangles here. It's way easy to find relationships between theta and L1 and theta and L2. Right triangle, I know the opposite side in this right triangle. I know it's 6 from the coordinate of the point, or remember we had a 6-foot wide hall here. So we've got 6 for the opposite, L1 for the hypotenuse as relates to theta. So the sine of theta is 6 over L1. Over here, we've got the adjacent of this in this right triangle and L2. Is the hypotenuse. Adjacent and hypotenuse, well, then the cosine of theta is 8 over L2. So there's a relationship between theta and L1 and theta and L2. We're interested in L1 plus L2. We're interested in the length of the ladder. So let's solve this for L1 and solve this for L2 in terms of theta. And then we'll have the length of the ladder in terms of theta. Cross multiply, we get L1 equals 6 divided by sine theta from this little formula. From this little formula, cross multiply, you get L2 equals 8 divided by cosine theta. So when we wish to express the quantity of interest, the length of the ladder, as a function of theta, we get L of theta is L1, 6 over sine theta, plus L2, 8 over cosine theta. Let's write that 1 over sine as a cosecant and that 1 over cosine as a secant. So let's make those trig substitutions, those replacements, those trig identities that relate to the reciprocals of sines and cosines. Then I don't have to do any quotient rule stuff or something like that. I got to deal with differentiating secants and cosecants. Yeah, we've done plenty of that. So far, smooth sailing. So we got a picture. That was given as a hint. We got relationships. Those were easy relationships to get. We've dealt with significantly more complicated stuff than that relating to variables. And then we had the quantity of interest as a function of those thetas. And here it is. And it doesn't look like a complicated function. All right. Then the question has become, minimize. Remember, we were minimizing to find the longest length ladder that would go around the hallway. We're minimizing L of theta, and as we discussed, we want theta to be between 0 and pi halves. Ooh, I don't get to include the endpoints. All right. Here's L of theta from the previous slide. So, piece of cake, conceptually. We'll take the derivative. We'll find the critical points. We don't have endpoints, so we'll check increasing and decreasing as relates to those critical points. Well, it sounds easy enough. The trig functions are making this one a bit complicated. All right, well, derivatives. I ain't afraid of no derivatives. Piece of cake. You can differentiate cosecant and secant. Derivative of cosecant is, you kind of need to have these in your head because you're using it a lot these days. Derivative of cosecant is negative something. All the cofunctions, their derivatives started negative something. Derivative of cosecant is negative. It was cosecant, cotangent. Derivative of secant was secant tangent. So there's what we get for L prime of theta. Tell you what, let's convert it back into sines and cosines. That made the differentiation relatively easy, but you know, when the rubber hits the road and I'm going to set this equal to 0, I'd prefer to deal with sines and cosines. So we'll take the cosecant and write it as 1 over sine, the cotangent and write it as cosine over sine. Similarly, over here with the secant and the tangent. In terms of sines and cosines, we get this as the derivative. Let's clean that up a little bitty bit. We got a sine squared here in the denominator and a cosine squared there in the denominator. So that produces this. Just simplifying, let's get a common denominator, as you often do when solving equations. We'll multiply this by cosine squared over cosine squared, multiply this by sine squared over sine squared, giving us the common denominator of the product of the squares of the two trig functions. We'll have a -6 cosine cubed, and we'll have a +8 sine cubed. We multiplied by squared trig functions over themselves. That produces this. We just need to find critical points in the interval 0 to pi halves. First off, no critical points where L prime is undefined between 0 and pi halves. Between 0 and pi halves, these are acute angles. The sines and cosines are not 0. The denominator doesn't cause any problems. So, you know, it's a good thing we threw out 0 and pi halves. If we hadn't, we'd have some problems here. So, no critical points in the open interval. No division by 0 over this interval. There's division 0 elsewhere, but not here. So, when is the derivative equal to 0? When the numerator is equal to 0. So we need to deal with this. -6 cosine cubed theta plus 8 sine cubed theta equals 0. You have experience in solving for theta in trig equations. And I'm sure you've been exposed to something like this in your previous travels, but you might be a little rusty at this. Let's follow our nose here. From this equation, we could take, say, the -6 cosine cubed to the other side. The equation becomes 8 sine cubed equals 6 cosine cubed of theta. How about this? Let's take the 8 to the right-hand side in the denominator. That'd give us 6 over 8, or 3 over 4. And let's take the cosine cubed to the denominator of the left. Kind of cross multiplication backwards. We're dividing both sides by 8 cosine cubed theta is what we're doing. And that produces this. So we get the cosine cubed over here. We get the 6/8, well, 3/4 over here. And what we've accomplished there is, hey, sine over cosine is tangent. So you're dealing with tangent cubed theta equals 3/4. That you can deal with. All right. We'll take cube roots of both sides. Cube rooting is a 1-to-1 function. We'll get all the solutions. And we get tangent theta equals the cube root of 3/4. Does this ring a bell as a special angle? Not with a cube root in it, no. Maybe square root of 3 over 2, but that's not what you got. You got a cube root, so there's nothing special about this, which makes the following a bit of a challenge. But I can say theta is then the tangent inverse of this number. This number is between what, 0 and 1? So this angle we're getting out, it's an acute angle. So we're getting an acute angle out. In fact, I think we're getting an angle out between 0 and pi/4, if I'm thinking correctly. Let's check on that. That's a good thing to check on. All right, the tangent inverse function, it's an increasing function. It looks like a really stretched out S. It's an increasing function. It's increasing on the whole real line. You could check its derivative. 1 over 1 plus x squared. That checks as being always positive. This is an increasing function. you know from differentiating it, or you know just from the graph of it in your previous experience. So I'm about to make some, on the surface of it, really unmotivated observations. Let's take something less than the cube root of 3/4. How about the cube root of 3/8? That's less. I mean, 3/8 is less than 3/4. So the cube root of 3/8 is less than the cube root of 3/4. The tangent inverse function is an increasing function, so it'll preserve those inequalities. And the tangent inverse of the cube root of 3/8 is less than the tangent inverse of the cube root of 3/4. You got the background to believe that. A reasonable question is what the hell am I up to with this? I'm looking for test values that we're going to need in a table because I don't have endpoints. So the absence of endpoints is putting us through this. How about something bigger than the cube root of 3/4? That's 1. If you like, the cube root of 4/4, 1. This quantity is less than 1. So the tangent inverse of the cube root of 3/4 is less than the tangent inverse of the cube root of 4/4. I pick something bigger to put in the tangent inverse function. It's an increasing function. I get something bigger out. But this time I actually know what it is. Cube root of 4/4 is 1. The tangent inverse of 1, that's pi-4. So we're going to use the tangent inverse of the cube root of 3/8 and pi-4. We're going to use those two values for test values in a little while. They're in the right place. I got to compare them to this angle. Tangent inverse cube root of 3/4. Yeah, pi-4 is bigger than that, as we just argued, and this thing here is less than that. And also this thing here is positive. So I am indeed picking two numbers, this one and pi-4, that are in the appropriate places. A trigonometric side trip that we didn't have to do now, but if we don't do it now, we're going to have to do it on the next slide. So here's where we are. We've found the derivative. Denominator is always positive, by the way, because it involves things squared. These things are non-zero over this interval. So the sign of this is entirely determined by that numerator. Okay. Let's take theta sub k. That's that test value. We represented test values with k, so I'll put a subscript of k on this. Let's take theta sub k to be the tangent inverse of the cube root of 3/8. Tangent inverse cube root of 3/8. Then we'll have the tangent of theta sub k, take the tangent of both sides, is the cube root of 3/8. Cube that, you get 3/8. Convert it into sines and cosines, you get this. Cross multiply, you'll get sine theta is 3/8 cosine theta sub k. Plug that into this numerator. I'm looking for a sine in all of this. Plug that into the numerator. The numerator is -6 cosine cubed of theta. We're plugging in theta sub k. Plus 8 sine cubed theta. We're plugging in theta sub k. And that produces, since we saw that the sine of theta sub k is related to the cosine of theta sub k by this, produces, you might want to think this through. Pause and think this through. Numerically, it's this. If you'll simplify this, we've got 3 cubed is 27. 8 cubed is, well, it's 64 times 8, but we got an 8 in the numerator. We get a 64 in the denominator. I need a common denominator with a 6. It'll produce this ugly coefficient. Anyhow, that's negative. So the reason we got into this stuff with the tangent inverse of the cube root of 3/8 on the previous slide was to get this simple computation. It's simple because I was able to do it. So, I mean, the numbers are ugly, but we got a negative number out of this. Excellent. That'll be useful in increasing, decreasing information. So when we take L prime and evaluate it at this angle, we get something negative out. The numerator's negative, as we showed. Denominator's always positive over the interval 0 to pi-halves. Now let's choose something bigger than the critical point. And we said last time, let's use pi-4. That was the last slide, the computation that was relatively easy. You plug pi force in. You know the sine and cosine of pi force, so I don't have to go through this exotic manipulation on that. We can just plug that one in because that's a clean angle. And it'll produce 2 times square root of 2 over 2 cubed. Yeah, square root of 2 over 2 for sines and cosines of pi force. That should sound familiar. It produces this. Anyhow, that's positive. So the derivative at pi force is positive. I appreciate your support and patience. So what's going on? We had a critical point given by this number here. Tangent inverse of the cube root of 3/4. We're looking at the interval 0 to pi halves. So let's take that interval 0 to pi halves and remove the critical point. And let's look at first derivative information. We need test values. Pick a test value between 0 and the tangent inverse of the cube root of 3/4. We use that one. And we saw when we plugged that into the derivative, here it is, we got a negative number out. Negative. That function's decreasing. Pick something from here. We've seen that pi force is in this interval. When we plug pi force in, I can actually tell you the value this time of the numerator at least, we get that out. That's positive. The derivative is positive at pi force, and the function is increasing. Okay, my apologies. This is a standard problem. I'm analyzing it without any intuition and doing all the work. That made the last slide in this slide inordinately complicated with this cube root of 3/4 and cube root of 3/8 stuff. But anyhow, if you'll at least buy the fact that the function goes down and then up, oh, the first derivative test says that's a minimum. It went down and then up, minimum. We were looking for a minimum. First derivative test for local extrema, theorem 4.3.a for the record, says L has a minimum at that critical point, at that theta value. All right, so when they didn't ask us anything about theta, they asked us about L. What is the minimum length? Remember they wanted it to the nearest foot? All right, so now I got to take theta, substitute it back into L, and express the length in terms of this information. All right. We had length expressed in terms of secants and cosecants of theta. I think we can find those from tangent information. If we got theta equals the tangent inverse of the cube root of 3/4, then we got the tangent of theta equals the cube root of 3/4. We said that earlier. You know the trig identity, 1 plus tangent squared equals secant squared. Okay, well, here we've got theta with a tangent of this. So we'll plug that in this formula, and that'll give us a secant squared, and we need the secant. Taking reciprocals, if you like, 1 over secant squared is cosine squared. 1 over this is what we've got down here. Taking the 2 inside and squared these two. 3 squared is 9 and 4 squared is 16. That's where this came from. We can multiply by the cube root of 16 over itself to eliminate the compound fraction. Cube root of 16, let's see, 16 is 8 times 2, and the cube root of 8 is 2. You can bring some 2's out front of this if you want to simplify it a little bit. I don't mind really leaving it like that. Take a square root, take a positive square root. You know this cosine is greater than 0 because we're dealing with an acute angle. Don't take the negative square root of sine, but we've got reasons for that. And we get the cosine of theta is this icky quantity here. Hey, if you got the cosine, I bet you can find the sine. And we can invert this and get a secant, depending on how we want to approach it. Sine squared equals 1 minus cosine squared. So let's plug that cosine we just found in. It gets squared, so I lose the square root. Gives us this. Trust me on the arithmetic at this late hour. Simplifies to this. So we could find the sine of theta by taking a positive square root of this. What that would produce is the the reciprocal of this quantity. I didn't stick that part in. We got sine squared theta equal to this, so you can find the sine of theta by taking square roots. So at the critical point, we had L of theta expressed, say, as 6 over sine theta plus 8 over cosine theta. I know we also wrote it as in terms of secants and cosecants, so we could have left it that way and not had to take reciprocals, but 6 of one, half dozen of the other. Sine of theta, that's this. So 1 over sine theta would be the reciprocal of this, which is written here with the square root introduced. Right, this was sine squared with the square root introduced. Cosine theta, it's given here. We'd substitute it in here, take a reciprocal, that produces this. And there's an exact value. Let me clean it up a little bitty bit by taking this cube root of 9 into the numerator. And I'm pretty much stuck with that cube root of 9. I'm just putting it somewhere else. That produces this. And by the way, if you look at this, that's not that bad. Geez, it's got cube roots inside of square roots and some stuff added together. It could be worse. All the trig stuff's gone is the good news, but we got rid of all the trig stuff and produces something like this. To answer their question, let's get the calculator out. Not until we've got the precise value, or else we're building round-off error upon round-off error. This is approximately 19.7 some odd. We were looking for a minimum length ladder that would go around the corner. Yeah, 19.7 some odd. They wanted it to the nearest foot, then round down. You round up, the ladder will be too long to go around the corner. A 20-foot ladder won't go around the corner, but a 19-foot one will if you want it to the nearest foot. And I've been doing this a long time, and this has got to be the worst, most complicated max-min problem, but I've got all the details spelled out for you here in this solution. Bad test question, way too long. The last couple of them were bad test questions, but the idea, still the same. We got a function of something, it was theta in this case, and we minimized it. Okay, we didn't have endpoints on an interval, so we had to do some first derivative test stuff. Yeah, well, that make things a little bit involved, but all the details are here. Okay, let's jump back to the notes. There was one final, you're gonna like this last one. There was one final observation in the notes from this section, and it dealt with kind of business applications or economic applications. It says, let X be the number of items produced and sold by a business. Let R of X be the revenue that results from selling the items, and let C of X be the cost of producing these items. These are called cost functions and revenue functions, respectively. The profit function, profit is revenue minus cost, makes sense, the amount of money you bring in minus the amount of money you spent to produce. Economists and economics is actually fairly involved math-wise, but economists call the derivatives of these functions the marginal revenue, cost, and profit, respectively. So economists use the word marginal for derivative, but they're just derivatives. But that's the verbiage. I just introduced this so you'll have exposure to it. The average cost function is the cost function divided by X, the number of items produced and sold. So it makes sense. You take the total cost and divide it by the number of items involved. If R and C, revenue and cost functions, are differentiable and X can be any value, then profit will be maximized when the profit function, that is the marginal profit function, that is the marginal revenue function minus the marginal cost function, equals 0. Yeah. You take the derivative and you set it equal to 0, except in this setting you call derivatives marginal functions. But still, of course, you set the derivative equal to 0. So that's the production level that will yield maximum profit, also minimum profit. And of course, it occurs when the marginal revenue function and the marginal cost function are equal to each other, simply setting this equal to 0. So there's some sort of show-offy words from another setting. Yeah, you get extreme where the derivative is 0. And this goes through and compares cost functions with revenue functions. When cost and revenue are the same, you're at a break-even point, so you're not losing money. If you're spending more, if cost is greater than revenue, spending more than you're bringing in, then you're losing money. You break even. If you can get cost below revenue, then you're making money. They're furthest distance apart when you're maximizing profit. Revenue minus cost, the distance between the yellow curve to the blue curve, that was when the yellow curve's on top, that was profit. It's a negative of profit over here. So let's do one last example that illustrates that. The function will come to you. There won't be pictures to draw. We'll still attempt to follow those steps, but it will be a much more manageable question. For some more hostile questions, there's a bunch of examples in the book. I strongly suggest you read this section of the book, you read through the examples. They give you those steps that I've introduced, and I've intentionally not done any of the examples in the book because you have access to the book and you can read those examples there. This ain't easy, not for the faint of heart. This is, in my experience, this and related rates are the two things that students struggle with most in Calculus 1. It's sad news. That's the applications of Calculus 1 that you encounter in Calculus 1. Arguably, along with some of the velocity and acceleration stuff. You could say those were applications as well. But this is the most common applications of Calculus 1. So let's look at this last question. They give us a cost function. Suppose that C of x is x cubed minus 20x squared plus 20,000x. This is the cost of manufacturing x items. Find a production level that will minimize the average cost, C of x divided by x, of making these x items. Okay, no picture. They gave us the functions. They gave us the variables. So we're good to go on this one. They want us, step 4, to minimize the average cost function. Average cost, let me call it capital A to give it a single letter representation. It's the cost function divided by x. Here's the cost function. Take that divided by x, produces this average cost function. You like that function, don't you? Yeah, mercifully, it's just a second degree polynomial. Its graph is a parabola, an opening upward parabola, by the way. So the question is, minimize that function for x between 0 and infinity. X can't be 0. We've divided by x up here, so that gets thrown out. So you have to make something, or the average cost isn't defined. Of course, there's physical reasons you can't make larger and larger amounts of things, but we'll take the interval 0 to infinity. And remember, it's an opening upward parabola. The critical point will correspond to a minimum. The derivative, now we're cooking. Derivative is 2x minus 20. So x equals 10 is the only critical point, making the derivative 0. Let's throw something a little bit different at this one. Is it a local maximum or a local minimum? Or neither. How about we use the second derivative? The second derivative, it's the first time we've done this in this section. The second derivative is just 2. So this function is concave up at this critical point. The second derivative test for local extrema tells you you've got a local minimum. Second derivative is positive, local minimum, concave up. Remember the double plus sign smiley face? When we first encountered concavity, I called them concavity emojis. Yeah, that's the second derivative test for local extrema. That's what this theorem 4.5 really is. Yeah, we check the second derivative. It's positive. It's a smiley face, concave up. The critical point will correspond to a minimum. And there aren't any other critical points. So this local minimum actually must be an absolute minimum. And the level of production that minimizes average cost must be x equals 10 items, whatever the items are. They didn't give us units. And that takes care of 4.6, applied optimization. And that's probably one of the rougher spots in Calculus 1. But we'll continue on, finish up chapter 4. We've got some numerical stuff to do in the next section. In the last section of chapter 4, we'll be shifting gears into preparation for chapter 5, which is the third and final big topic of Calculus 1. which is integration. The big topics of calculus 1s are limits. We did limits and we used limits. Derivatives, we did derivatives and we used derivatives. We're in the middle of applications of derivatives now. And integrals. And a question about how integration relates to differentiation. We'll elaborate on that in chapter 4 as well. It's the last thing we'll do in chapter 4. Have a nice day. I'll see you in the next section soon.